Hello, everybody. Welcome to the Coffee Science Seminar Series. Anthony, you can hear me, can you? Yep.
Okay. Yes, I can, Craig.
Thanks a lot. Sorry about that. It's my pleasure today to facilitate this seminar presented by Anthony. Do you want to move on to the next slide, please, Anthony?
Yep, and just my screen seems to have locked. There we go.
Okay, sorry, this is a bit clunky, but we'll get into it. Okay, so my name's Craig Hardner, and most of you probably know that I work with the Centre of Horticultural Science and in horticultural genetics. Could you move to the next slide? So I want to start by acknowledging the traditional owners and custodians of the lands on which we meet today, and also those lands where those listening are today. I would like to pay my respects, and on behalf of all of us, our respects to their ancestors and descendants who continue cultural and spiritual connections to country. We recognise their valuable contributions to Australian and global society. Thanks, Anthony. So just to remind you of the format of today, Anthony will present, and it's scheduled from 12 to 1. It's about half an hour to 40 minutes of presentation. And then after the presentation, we'll hold question and answer session. It's important that you put your questions and answers into the question and answer box down below rather than the chat function. Okay, can you go to the next slide? So Anthony, I've known Anthony for quite a number of years, and he previously, when we both worked together in CSIRO, and then after coming, then he continued, I came over to UQ in 2007, but he was continuing his role at CSIRO as the CSIRO state business development manager, which led to the formation of several alliances in health, energy, food and marine research. But Anthony's fundamental passion is agriculture, and he moved back into agricultural science roles, particularly at UQ in 2016, and is undertaking work on a number of crops, two of which he'll talk about today, macadamia and avocado. Myself and Anthony got involved in the macadamia work about 4 or 5 years ago when I had had a small role in a harvest review project for macadamia, and Anthony helped me there, and then started to develop some of the ideas he's going to talk about today. So Anthony, after that clunky start, I'll leave it over to you, and we'll have a chat at the end. Thanks.
All right, thanks for that, Craig. And I too would like to acknowledge the traditional owners and their custodianship of the lands on which we meet. And I would like to pay respects to their elders past and present. Sorry, this is just behaving a little bit clunky here, and it won't move on to the next slide. Worked perfectly in practice. There we go. As Craig said, I just wanted to share with you today 3 small pieces of work in 2 crops, macadamia and avocado. Most of my work's been done in broadacre crops, but since coming back into science and doing some work at UQ, I've been working in horticultural tree crops as well. And certainly I've enjoyed not having to wear suits and ties as much as I did when I was Queensland State Manager for CSIRO. So the 3 forays into tree crop physiology. As Craig mentioned, the first one was a desktop review of ways to manage harvest period of macadamia. And I was looking at issues to do with synchrony of nut drop and ways in which we could manipulate that. And it was essentially a desktop review. Then the second area of work was a small project looking at can photothermal quotient be used to understand the yield variation in macadamia. And I'll talk a bit about the relationships between photothermal quotient and yield. Look at the productivity and water use of macadamia, and finish off with VPD effects. And then lastly, a project that I got involved with CSIRO from Adelaide, Harley Smith, looking at carbohydrate monitoring to predict yield in avocado. So I'll talk a bit about relationships between yield and PTQ, stem and branch carbohydrate, and then characterisation, what we can learn from characterisation of avocado growing regions. I'll just move that down a bit. Oh, there we go. It's moved sideways. So, very briefly, just a schematic of the growth cycle of macadamia. Crops flower usually in the window of around August to October, followed by nut growth or some premature nut fall where the crop load is adjusted according to the conditions. Nut growth and oil accumulation mainly through December, January, February, and then nut drop starts somewhere around towards the end of February through to June. And nuts are collected in macadamia by picking them up off the ground. So the growers wait for the nuts to fall, and then nuts are swept up and collected in various passes. And you can see that there can be 4 or 5 passes during that nut drop period where the farmer has to go around and pick up the nuts. The industry identified, so this project was a hort innovation project, MC 16001, a review of harvest systems and options. A more efficient harvest would involve fewer passes and would reduce the cost of harvest. Because the nuts wouldn't be laying on the ground for as long, there'd be less problems with fungal issues and less predation by animals. It would also improve scheduling and timeliness of post-harvest orchard activities. There's a little bit of evidence that the earlier, shorter harvest improves yield in the following season. And ethifon, which is a precursor to ethylene, a ripening agent in plants, is in commercial use, but the results are variable. So I'll just talk about a small area of this work, and that was where I focused on understanding the retention and abscission of plant organs, leaves and nuts, but obviously in this situation, the focus was the nuts. What became evident was that our knowledge of retention and abscission is incomplete. And what we do know is that abscission occurs at a predetermined abscission zone, and metabolically active organs, such as leaves and fruits, produce auxin, which then diffuses from the fruit or leaf back towards the stem of the crop. And that diffusion gradient, while it's present and while the auxin is being produced, maintains that abscission zone in a non-responsive state. And it doesn't matter what you put on them in terms of, or how much ethifon you put on them, they won't abscise and fall off. What seems to be the trigger is a decline in the synthesis and transport of auxin, and the lack of that diffusion gradient is then followed by an elevation of ethylene and abscisic acid. The abscission zone goes through some changes and becomes responsive to ethylene, And so the decreasing oxygen provides a stimulus for the initiation of the abscission cascades, or a series of metabolic processes that leads to the nut falling off. And I guess what we were really interested in was, where we think some future research could focus is, how can we trigger that abscission cascade to make the nuts receptive to ethophon? This is a diagram which I took from a publication by Gonzalez and Carranza, and just modified that slightly. And you can, if I just walk you through it, while auxins are being produced and are diffusing from the fruit side through the abscission zone here and to the proximal, then that gradient of auxin inhibits the development of that abscission zone. And the key inhibitors are the active growth of the fruit or the leaf, active photosynthesis in that area, lower temperature and demand for assimilant. But as the auxin decreases and the ethylene increases, we can see that the abscission zone becomes responsive and the nut can fall off. Stimuli to that sort of thing is wounding, heat stress, drought stress, reduced photosynthesis, senescence, darkness, and fruit ripening. So the conclusions from this brief bit of desktop research was that we need to do some more research to better understand the process. And if we're to make any real gains in macadamia, we have to understand why there's a lack of synchrony in that abscission of the nuts. Why is it that even though the nuts are mature and they reach their maximum oil content, why is it that some nuts will drop off early and then over the next 4 months? Why are those nuts that are retained not responsive to ethylene? And so there's a few places that I think we could start. And one is, what's the source of the auxin in the mature nuts? And I guess I'm proposing that it's probably the green husk where the auxin's produced and then diffuses back through the peduncle. And how can we make that abscission zone receptive to the ripening agents and initiate that cascade? So just a brief foray there into some of the issues to do with macadamia nut abscission and what we learnt from that short project. The next one was a project which was Coffee DAF collaboration seed money that Craig and I, together with Shane Mulo from DAF, applied for some of that money to look at whether photothermal quotient can explain yield variation and premature nut drop in macadamia. It was only a short project, and so we chose and rationalised that with improvements in field weighing and affordable GPS, that we would try and get access to grower data. And if we could get access to the best growers in the various regions, then that should give us pretty reasonable estimates of what potential yield in those regions are. There's two approaches to looking at this. One is to look at multiple years in one location, which might reduce some of the confounding effects of different soil types, different slopes, radiation, different water holding capacity of the soil. And so we can look at a number of years of data from the one site for a range of growers. And we were able to tap into the DAF benchmarking project and approached a number of growers in that top 25% of growers, and 11 growers got back to us and said that they were willing to share their yield data with us. The other approach is to look at multiple years in multiple locations. And in this way, you might increase the signal or the variation in the photothermal quotient and see if you can, if that enables you to pick up more of a relationship with photothermal quotient. But as I mentioned a moment ago, there are issues of different soil type, different water holding capacity, different management that might add to the noise and limit your ability to see any relationships there. So that we tapped in again to the DAF Series 3 regional variety trials across sites and seasons. So just quickly, what is photothermal quotient? And I had this slide in at the beginning of the talk for a while, but I've figured out this was probably the best place to put it. Photothermal quotient is a surrogate, or can be a surrogate, for the assimilant supply available to the crop per unit of development. And if you look at this equation at the bottom here, the daily radiation provides the energy that allows the plants to photosynthesize, and so it's the amount of assimilant that's available to the crop. The denominator, you can see here, is the average daily temperature, so the maximum plus the minimum divided by 2, and then minus a base temperature. And the base temperature is characteristic for the crop. For wheat, it's typically around 0. For macadamia, it happens to be up around 10, and avocado seems to be about the same. The denominator here is what's called the simple method for calculating thermal time. And so it's a rate of development for the crop. And this simple method works surprisingly well, and as well as some more complex methods for calculating thermal time. But I just ask you to remember that because it did cause us some problems as we got into this work further. So photothermal quotient can be used to investigate critical growth periods that affect yield. A higher value equals conditions that are more favourable to growth. And it works best if biotic and abiotic constraints are minimised. That is, the crop is yielding somewhere near its physiological potential for that region. And there's a couple of examples in wheat that I'll just show you here. One by Rawson, another one by Peake and Angus. Rawson looked at a whole range of publications and expressed calculated the photothermal quotient for each of those experiments around the world, and then plotted the grain yield from those experiments. And you can see this relationship here, that as photothermal quotient increased, there was an increase in the grain yield at those sites. I mentioned a moment ago about crops yielding somewhere near their potential. These 2 points here, so at the bottom of that red arrow to the top of the red arrow, the bottom of the arrow was no nitrogen applied to a wheat crop in the Netherlands, and by applying 150 units of nitrogen, you can see they took the yield of that treatment up to just above the line. And so the less constraints there are, the better the fit that you will see, or the better the relationship you'll see between yield and photothermal quotient. Just a bit of data of my own that I've been having a look at more closely lately and preparing a publication for. This is a grain yield of wheat over a number of sites and years, and the nitrogen uptake of those crops. And you can see there's some interesting curves there as grain yield is related to nitrogen uptake. But if we correct all of those yields to a constant or same photothermal quotient of 1.5, then you can see that the sites that were well watered and well managed fall onto a response curve. And in the 3 sites where we had terminal drought and there was water stress at the end of the season, you can see those experiments fall away from that yield envelope. So you can see if you've got the right situation, you can learn some pretty interesting things by employing the use of photothermal quotient. Now, I want to just briefly tell you about problems with base temperature in cooler environments. When we calculated this as a year's data, a year's weather data, On the x-axis, minimum temperature each night, and on the y-axis, the photothermal quotient for that day. And you can see at Atherton, where temperatures are generally fairly warm, that whether you have a base temperature of 0, 5 or 10, the response is fairly linear. A couple of points there that sort of fall above the rest, but pretty good. But when you go to somewhere like Alstonville, you can see that as you go to higher base temperatures, then the photothermal quotient becomes non-linear at low minimum temperatures. And that is nonsensical, and some values are even greater than are expressed on this graph here. And so that led me to start wondering what's going on. I consulted with some scientists at CSIRO, Jeremy Wish and Julianne Lilly, who were doing some work in canola, and sat down and had a cup of coffee and discussed this. And what we figured out is that where crops are growing at temperatures above their base temperature, so base temperature runs through here at 10 degrees, and the minimum and the maximums are above that temperature, then the simple method does a very good job of estimating the daily increment. So 11 degrees plus 25 is 36, divided by 2 is 18, minus the base temperature of 10 gives you a daily increment of thermal time of 8 degrees. But what happens, what happens when you go to lower temperatures? And here you can see the base temperature of 10, and the temperature only gets above the base temperature for a small period during the day. And so when you use the simple method, you get a value of minus 2.5, and development can't go backwards. So that's just corrected to about a daily increment of 0 degrees. But that's what leads to some of these nonsensical values. When these values get to somewhere around 0, then the denominator becomes very small, and when you divide the radiation by the denominator, you get these ridiculously high or low numbers. What Jeremy and Julianne were doing was dividing each 24-hour period up into 8 segments, and then fitting a circadian curve to that, and then only counting the amount of time in which the temperature was above the base temperature. And when you do that, you can see that you get in this particular example, you get a daily increment of 0.9 rather than 0. So at Atherton, where temperatures are generally warm, it doesn't make that much difference. But as you go to Alstonville, you can see on the right here is the segmented method, and on the left is the simple method. You can see that you get a much better estimate of the photothermal quotient. And when you go to somewhere like Untitled in Western Australia, where the temperatures are quite low, you can see that you get a vast improvement in the estimate of photothermal quotient. So this work is an interesting aside, and we'll be publishing that with the CSIRO because this is quite a new area of a way of looking at things. So when we looked at the yield of macadamia nut in shell for the regional variety trial series 3, and we calculated photothermal quotient in the pre-flowering period, 3 months, or the post-flowering period, 3 months, you can see that unfortunately there was no relationship there. And the reasons are many and varied, but probably one thing is the difference in size of the canopy of the trees. These trees are quite small, and they're not taking up all of the available space, and so tree size could be a factor. And so as we go through each year, yield is also increasing. So unfortunately, we didn't have much luck with that sort of data. And then with the other grower, the benchmarking trial with the growers, data, again, for pre and post flowering periods, the photothermal quotient did not show any relationship with the yield, nut and shell of macadamia. And this really got me in quiet moments wondering why, and letting off a few expletives as well. And it made me wonder, well, maybe macadamia is not as productive as it should be. And I had a couple of good conversations with Bruce Topp and John Wilkie, and they pointed me in the direction of this lovely small paper, conference paper by Stevenson and Chapman, where they compared the tree crop benchmarks of citrus and apple with other emerging tree crop species. And they express the yield on an energy equivalent basis, which is very important because there are varying amounts of carbohydrate and oil in the yield of these species. And, you know, they reasoned that the radiation input in a lot of these species is fairly similar, and so there shouldn't really be that much difference. But when you look at the harvest index for apple, it's quite often up around 0.65, whereas for the macadamia kernel, it's only around 0.17 or 0.5 in nut and shell. And that's why some of the focus is on reducing the thickness of the shell of macadamia. So here you can see the table where they looked at the energy in the fruit, the highest commercial yields, and the relative yield based on energy. And so you can see orange and apple are right up there. And unfortunately, because of this box, you can't see, there's macadamia at relative yield based on energy of only 30% of what orange and apple is. And so it really got me thinking about why that is the case. It also made me realise, well, that's probably why we're not seeing any relationship with photothermal quotient, because the crop's not yielding anywhere near its radiation limited potential. So I had a few discussions with some growers at different field days and things, and this is sort of a typical macadamia orchard, 312 trees per hectare, 8 metre spacing between the rows, 4 metre spacing between trees within the row, and the canopies sort of intermingle within the row, and there's typically usually a bit of a gap between the rows in the middle here. Best practice irrigation is micro sprinklers or drippers, but in this diagram I've shown micro sprinklers, and they typically throw with a radius of about 2 metres under the tree. And so when I was listening to people talking about irrigation in macadamia, I realised that they're really only talking about the wetted area. So growers typically irrigate with 70 litres of irrigation per day during the summer months, which is equivalent to about 5.6 millimetres of evaporation or water use on that wetted soil area under the sprinklers. But if you calculate that based on the area of the canopy, it's only about 2 millimetres of water use. And during this time, pan evaporation's usually up around 5.5 millimetres per day. So well-watered macadamia trees are really only using less than about 50% of pan evaporation. And so that then makes you again wonder and points towards a lower productivity. Daniel Manson from Sun Farm has done some really interesting work putting collars on trees and looking at sap flow. And this is a 3-day period showing the sap flow on the y-axis. And for fully lit trees, which are irrigated, you can see each morning the sap flow increases until about 10:30 or so. and then it's truncated and it wobbles around until about 3 o'clock in the afternoon, and then you get this nice smooth curve again as it goes down here. And the next day, it will do the same thing. And so water use is increasing as radiation increases, but it gets to a point where the system is truncated, and you start to wonder what's going on here. And some of the data that he has shown is that leaves are 2 to 4% hotter than the ambient temperature, which tells you that in this midday period, the leaves are closing their stomates, and because there's no evaporative cooling, the leaves are heating up. So the macadamia trees are closing down. Some really nice work by Smith et al., published 2020, showed that as VPD on the x-axis increased, then stomatal conductance was fairly constant up to around 2 kilopascals, and then above 2 kilopascals it dropped quite dramatically. And you can see here on the same measurements the leaf temperature increasing as the vapor pressure deficit increases. So these leaves, for whatever reason, are closing up at VPDs above 2 and closing their stomates and not making the best use of the water that they have available, and that is therefore limiting their potential to produce yield. So I went back to a number of the experiments, to a number of the growers' sets of data, and expressed pre-flowering VPD against the yield nut and shell and the post-flowering. And lo and behold, at one site, and I must admit this relationship looks nowhere near as good as this for a number of the other sites, but at this particular site, we see this negative linear effect that as VPD increases, then the yield of nuts, as it increases, the yield of nuts decrease. And that's quite a tight relationship, saying that, you know, indicating that the VPD that the crops experience has quite a dramatic effect on the yields. And so why doesn't macadamia work, PTQ work for macadamia? Is it the effect of previous season on the current crop? Is it plus or minus irrigation, local differences in canopy management, some biotic constraints, nutrient management? Well, I think from the work that I've done and from the literature I've looked at, it's certainly macadamia's stomatal response to VPD that's limiting its ability to yield. Now, what's causing the stomates to close? Is it an issue with hydraulic conductivity in the tree, perhaps in the leaf petioles, or is it really that the stomates are just hypersensitive to VPD? And so again, you know, I'm proposing that we should be looking at management and breeding options to manage and overcome these stomatal constraints in macadamia. So now onto carbohydrate monitoring to predict yield in avocado. This was a 9-month forward innovation project led by Harley Smith, CSIRO in South Australia. And the review is really to look at non-destructive methods to monitor avocado tree carbohydrate. There's a real push in the avocado industry to monitor carbohydrates in the tree and use that as a management tool to try and optimize yield. So I had a discussion with Harley, and we were able to include Photothermal Quotient in the review. And Avocados Australia and Simon Newitt from DAF assisted with introductions to growers. We ended up, a little disappointingly, but we ended up with 6 growers that agreed to supply commercial yield data. But the positive was that many of those data sets were very good. Unfortunately, we found the same thing in avocado as we did for macadamia, that when we express photothermal quotient against yield, the pre-anthesis photothermal quotient or the post-anthesis photothermal quotient did not relate to yield. With the benefit of knowing what we found with macadamia, we looked at VPD and its possible association with yield, and again, there was no effect there. So why doesn't it work for avocado? The thing I noticed about many of the data sets that we got from growers was there were environmental extremes or biotic events that in one year or another led to problems with yield at each individual site. Possibly differences in nutrient management, and of course that these are tree crops. They have vegetative and root flushes. There are alternative sinks to the carbohydrate, and those sinks may compete with yield at various times during the season. In avocado, I think it's probably a combination of all of those. There was nothing that really stood out to me. But because of the project's emphasis on in-season associations or measurement, non-destructive measurements of carbohydrate status, I started thinking about where I could actually find some data that might actually help me with that. And so I found 3 publications, 2 in avocado and 1 actually in macadamia. But sorry, before I go to that, I just need to give you a little tutorial in tree architecture. The main above ground part of a tree is the trunk. That separates into branches, larger branches, and then just before you get to the leaves are the small stems which hold the leaves. And so some of the data that I'm about to show you is from leaf stems and other is from branches, and that's important just to keep in mind. So this is a publication from Liu et al, and it's from 2.5 years of data from avocado trees grown at Irvine in California. And so we've got data along the bottom, and we've got stem starch in red here, and I was able to get onto the internet and find the weather data files for this specific period in that area of California, and go through the process of calculating photothermal quotient and then plot that on the same graph. And as you can see, and I don't think I'm using my imagination, I haven't done a proper statistical analysis on this yet, but there is quite a nice association of the starch content tracking with the photothermal quotient as we move through this 2.5 year period. Now, this is starch in the stems, so close to the leaves, and you'll see that the starch pretty much follows the photothermal quotient, and the peak is occurring at about the same time as the peak in photothermal quotient. When you look at starch in the trunk, so the red symbols, and the leaf in the green symbols, sorry, you can see that relationship, while it is still present, is nowhere near as good as it is for the stems. Then there was a publication, 3 years data from Schofield et al. From Mildura in Australia, and I did the same thing, got the weather files, calculated PTQ and plotted that against the data presented in the publications. And you can see here that, again, the starch in the branches is going up and down with the photothermal quotient, but there is a lag, and that lag plausibly is because the branches are further away from the source, and possibly the stems fill up with starch before the starch makes its way further down the phloem into the branches. And just to give you a bit of an idea of what that looks like, if you remove that lag, that 60-day lag period, you can see that the starch content tracks pretty well with the photothermal quotient that those trees were experiencing. It made me wonder what's going on with macadamia, and so I managed to find one publication by Stevenson and al. Where they looked at trees at Nambour, again over a 3-year period. And while the data is noisier, it still tends to go up during periods of high photothermal quotient and down during periods of low photothermal quotient. So again, possibly encouraging for macadamia as well. So the photothermal quotient got me thinking a bit about environmental characterisation for avocado, and we're getting a bit short of time. So this is very complex, but it's really a look at the different environmental variables that the trees are growing in at Atherton, Rockhampton, Alstonville and Loxton. But if you just look at the green triangles, which is photothermal quotient, you can see that at Atherton, it never really gets above about 15 day degrees, megajoules per day degree. Once we move through to Alstonville, it's getting a bit higher, and then to Loxton in South Australia, you can see that this period is quite high. What's common to these is that the peak flowering period, denoted by this blue symbol, tends to occur just after the peak in photothermal quotient. And so that's really just the take-home message from that. So what does the long-term mean weather tell us, and what does this environmental characterisation tell us? It tells us that favourable photothermal quotient in the months leading up to flowering, and that raised photothermal quotient assists in flowering and fruit set and growth of the floral parts and storage of non-structural carbohydrates that are in excess for the growth demands. Those carbohydrate reserves are more than likely mobilised during fruit filling period to augment the current assimilate. Interestingly, the photothermal quotient during summer and into autumn is lower, and that's at the period of time when there's a greatest demand for assimilate to fill the fruit or the nut. And so the seasonal variation in photothermal quotient appears to favour a large flush of flowers, followed by episodes of premature fruit drop to adjust the yield potential to a more rapid rate of growth and development as the temperatures warm. So the post-flowering photothermal quotient displayed less interannual variation than the pre-flowering photothermal quotient. And that further suggests that the pre-flowering accumulation of soluble carbohydrate in that period and the lead up to flowering is more important than what happens post-flowering in terms of the assimilation and remobilisation. So just the conclusions. For macadamia, more research to better understand the abscission process. We could focus on what's the source of auxins in macadamia, and are there ways in which we can make the abscission zone receptive to ripening agents. Macadamia's response to VPG, the hydraulic conductivity in the tree is what's causing the lack of yield or the lower yield in macadamia. And so you could expect that for the crop to become more responsive as the domestication and there's more of a focus on productivity. And we should be looking at management breeding to overcome these stomatal constraints, either with the current germplasm or with future germplasm. And for avocado, reanalysis of the previous data was encouraging, and it confirms that PTQ could be used as a non-destructive surrogate for carbohydrate status of avocado trees in season. and further investigation of associations between carbohydrate status, photothermal quotient, and yield components would be desirable. Quick look at some of the people that assisted through discussions, pointing me in the right direction. As I said, I had a history in broadacre agriculture, and so working with tree crops was a pretty steep learning curve, and I'd like to acknowledge discussions and assistance that I received from all of these people. The alternative title for this talk was New Light Through Old Windows, so I just had to throw that picture in there at the end. And I'll turn it back to Craig and open it up for some questions.
Great, Anthony. Can you, I think there's, yep, question and answer slide. Excellent. So, yeah, as this slide indicates, now's the time that we've got to open it up to questions for Anthony. And I guess perhaps I'll lead off with my for a first question. And have you got a concept of a model of linking photothermal quotient or a similar, or carbohydrate production with abscission?
Yeah, interesting question, because there is a bit of data from Western Australia that was collected that, well, Lisa McFadgen's work, suggested that periods of low assimilation could lead to premature nut drop events. In avocado, we actually saw some evidence from Harley's earlier work that it was VPD that was associated with fruit drop events, so high VPD events causing high evaporative demand. But certainly what you mentioned, association of photothermal quotient with nut drop, you could expect that if there was a period of very cloudy weather, low radiation, and you had a high crop load, that could lead to some nuts being starved of carbohydrate and could initiate a nut drop event.
Yep. I want to just explore that. I wonder how, or have you got a feeling of how responsive then plants would be to that photothermal quotient? I mean, you talked about some of this storage carbohydrate and that being utilised, further on, but then, we're talking about those more immediate processes of carbohydrate assimilation. Yeah, have you got a comment about the sort of that delay or the immediate impact of constraints to carbohydrate production?
Yeah, look, I don't usually like to anthropomorphise, but it makes it a bit easier to explain. The higher photothermal quotient in the period leading up to flowering sets both avocado and macadamia up for a good flowering event and a high fruit set. But then once the assimilate demand from those nuts starts to kick in and those nuts really start to grow, we're entering a period where photothermal quotient starts to decrease. And I think the trees really are calling on some of those reserves that they're mobilising and the current photosynthesis that's coming through. If you did experience, periods of very cloudy weather or drought stress or VPD that limited the crop's ability to photosynthesize, then that lack of assimilate could actually initiate, starved nuts and fruits of carbohydrate, and it could actually result in them basically dying and dropping off.
Mm-hmm. Okay. Right.
So in a way, the tree is readjusting its fruit set, according to the conditions that are prevailing, and so there's this continual adjustment of the fruit set to the potential. Mm-hmm. Is one way to look at it.
Okay, great. like to encourage, we've only got a couple of minutes left, but like to encourage any questions if there are any. I'll just, finalise with one. The work by Stevenson and Chapman, and, that's been, talked about a lot, is that of looking at the yield potential. Does that, just from my understanding, does that account for the high oil content in macadamia?
Yes, it does. So when you express it on an energy equivalent or glucose equivalent,
Right.
you convert the oil to a glucose equivalent, and then you express that as the mass. So yes, they did go through and do that.
Yeah. Okay.
Yeah. So they were comparing apples with apples, so to speak.
Excellent. Okay. Look, we'll wrap up there, Anthony. Can you flick on to the next slide for me?
Sure.
So first of all, thanks very much, Anthony, for presenting the work. I mean, it's great to get for you to present this work to our collaborators in DAF and also to other people in coffee that are thinking about these areas, and certainly encourage anybody to have a chat with Anthony. He's just a couple of doors down from me, so some of you may know where I live. So I'd like to close with just announcing that we've got Bob Gilbert speaking next week. Bob's really graciously brought his seminar forward. We originally planned for the 16th of November, but we had a gap open up. So yesterday, Bob agreed to fill that. And I think, Bob's got his work in China, and he's sort of wrapping up some of his work here towards the end of the year. He can tell you more detail about that, but I'd really encourage everybody to join us next Tuesday to hear what Bob's got to say. So thanks very much.